Okay, I want to explain about modifying the ideal gas equation, the van der Waals equation. How can the ideal gas law be modified to yield an equation that will represent the experimental data more expertly? We begin by correcting an obvious defect and the ideal gas law, namely the prediction that under an infinity pressure and volume of the gas is zero at the absolute zero of temperature V same RT per V on cooling real gases liquidly and unlimitedly solidly after liquefaction, the volume does not change very much. We can arrange the new equation so that it predicts a finite positive volume for the gas at 0 Kelvin by adding a positive constanta V to the ideal volume and V same V plus RT and V. According to equation, the molar volume at 0 Kelvin is B and B is same 0 Kelvin, and we accept that B will roughly comparable with the molar volume of the liquid or solid. Equation also predict that as the pressure becomes infinite, the molar volume approaches of the limiting value V. This prediction is more in accord with experience than the prediction of the ideal gas law that the molar volume approaches zero at very high pressure. Now it would be interesting to see how well equation predict the curves in the fixed, and since by definition Z and V for RT. Multiplication of equation by V for RTL. And then Z and same 1 plus VV divide RT. Since equilibrium requires Z to be a linear function of pressure with a positive slope, V for RT is cannot possible with the curve of nitrogen in V, which starts from the origin with the negative slope. However, equation can represent the behavior of hydrogen. In V, the dashes line is plot of equation filtered of the origin of the core of hydrogen in the low pressure region, and thus this line represented the data very well. We can conclude from equation that the assumption that the molecules of a gas have finite size is significant of the explained value of Z greater than unity. Apparently, this size effect is the dominating one in producing deviation from ideality in hydrogen, and then hydrogen at um, T same T same 0 Celsius, and it is also clear that some other effect produce the deviation from ideality is gases such as nitrogen and methane. Since the size effect cannot explain their behavior in the low pressure range, this other effect must now be sought. We have already noted that the words of others in the matter of having value of Z less then unity are methane and carbon dioxide, so that methane CH4 and carbon dioxide, so that CO2, which are easily liquid. Thus, we begin to suspect a connection between case of liquefaction and the compressibility factor. And so as why a gas liquefies. First of all, energy, the heat of vaporization, must be supplied to take a molecule of the liquid and put it into the vapor. This energy is required because of the force of attraction acting between the molecule and its heat it bore in the liquid. The force of attraction is strong if the molecules are close together as they are in the liquid and very weak if the molecules are far apart as they are in the gas. The problem is to find an appropriate way of modifying the gas equation to take account of the effect of this weak attracting force. The pressure exerted by a gas on the walls of the container acts in an outward direction. Attractive forces between the molecules tend to pull them together, thus diminishing the outward thrust against the wall and reducing the pressure below that exerted by the ideal gas. This reduction in pressure should be proportional to the force of attraction between the molecules of the gas. Consider the small volume element T and V1 and V2 um, in a container of gas. Suppose that its volume element contains one molecule and that the attractive force between the two volume element is some small value F. If another molecule is added to V2, giving one molecule and V1, the force acting between the two elements should be Vf and V1 and V2, so that we have a same Vf. Addition of a third molecule to V2 and so increase the force to be 3m and so on. The force of attraction between the two volume elements is the proportional to concentration of two. The concentration of molecule in V2, uh, if at any point in the argument the number of molecules in N V2 is kept forces that is therefore proportional to concentration of number 1. The concentration of molecules in V1, thus the force acting between the two elements can be written as the forces concentration 1 and concentration 2. This is same. Since the concentration is a gas, it is very well the same. Concentration 1, same concentration 2, and concentration. And so, first, concentration 2, but concentration same mole for divide volume or 1 for divide volume. Consequently, for 1 for divide volume and then the writing in the form V same RT divide V minus V. Because of the attractive force between the molecules, the presence in the less than that given by equation by an amount proportional to 1 for V2. So a term is subtracted from the right hand side to yield.